What we're more interested, though, in general, is going to be tweaking the design, right? So I want to know the impact point that I'm aiming for. I've got a target, and I want to work backwards and say, so let's say they built that berm. Now it's, okay, really, how fast should I be launching myself off of this, or what angle should I be launching myself off of this to get the landing to work? Those would be the things that you'd change, the inputs to get the target output. Okay, so here's what we're going to try to do. We're going to be given the launch velocity height and a target x, and we're going to look for the launch angle. Is roots going to be the answer to this? Probably not, because what we have here is y equals, so we've got y naught plus r plus tan theta naught x minus of k 4.9 over cos squared v naught, cos squared theta naught v naught squared x squared. And what we're going to do here is define some of the variables. We're going to define y to be 0. We want the impact to be at height 0. We want the x to be at the target x. And this will be target x squared. And what we're going to not know is the angle. These are going to be the thing we're solving for. All right? We're going to know v naught. It's going to be fine. So we're going to know everything except for the angle in there and the angle in there. But it's still an equation. We want to solve it. Can we use, is this a quadratic in theta or a cubic, a polynomial in theta? Yes or no? Is there a theta naught squared? Is there a theta naught cubed? No. Where is it buried? Inside a tan. Where is it buried? Inside a cos in the denominator. No, it is definitely not a polynomial. And if as soon as it's not a polynomial, in that, remember, it's what you're solving for that defines it. We have many, many variables. The x's, absolutely. It was x and x squared with coefficients out front added together. That was a polynomial if I looked at it through the lens of x is my variable. But it's definitely not a polynomial in theta naught. And so roots is going to be completely useless, that roots command. It's a great thing if you have a polynomial, but we don't have coefficients. We can't define coefficients. We can't even make an input that makes any sense at all. So now we've gone from, in terms of equation space, we've gone from linear, which are nice, and then that's a subset of the polynomials. We've seen those with the roots, and now we're into the everything else. So that's the family of equations we can have to solve. Linear is great. Polynomials, pretty decent. We have a nice now piece of code that'll do that, the roots command. And then we get to the explosion of, oh my God, theta's in the bottom inside trig functions. Like there's just nothing nice about that at all. There's no way we can solve it by hand. Actually, there is a little way you can do it, but it's a lot of work. It doesn't look at first glance like we can solve it by hand. So what are we going to do? Well, let's make a target. Let's make the target 30 meters out. Right now, we're landing at about 40. So how would we do this if we have no other technology? We want to change the angle and have it land at 30 meters out instead of 40. So let's do a little bit of manual guessing and checking. What kind of angle might work better to land at 30 meters out? Go ahead, yeah. A larger angle. So let's try, give me a good number. 38. Excellent. So what we're doing is changing our input. For the love of God, 38, there we go. And rerunning it. And what I'd like to do down here is just take this semicolon off, so we'll see the impact value. There we go. We landed further away. Okay? So, but that gives us a hint, right? I was at 30. 38's going the wrong way, so I should go the other way. Someone yell out another number. That might be more.
17.
You guys don't yell very well. 17. Excellent. Which is good, I guess. Hey, it's like you were doing it before. All right. 17 degrees. That's actually pretty close. We land 30 meters out. But we can do better. We can do better.
16.
16. All right. And that is 29. Okay, this is going to be the first insight that we have for this. We've bracketed the distance. Somewhere between 16 and 17 degrees, there is an angle that'll land me exactly at 30. And if I only want 1 degree precision, that's fine. But presumably, where would be a next natural guess if I want to get closer to 30? 16.5, that's right. So in the absence of any other information whatsoever, halfway between two numbers that bracket it is a reasonable guess. And that gets us closer. But we're still a little bit on the low side, so we want to have a little bit of a higher angle. So maybe we went to 7.5. Split the difference again. And now we're down to landing within 1 centimeter of 30 meters. That's pretty accurate. But we could also do that again. We could say, all right, so between 17 and 75, we could go down to like 675, which is splitting the difference again. And then we're getting marginally closer again. So that kind of idea of get a bracket and then cut it in half, cut it in half, cut it in half, that's going to be our first serious nonlinear solver that we look at next week. And we will look at it next week.